to the Perimeter Institute quite a few times, and I've always found the visit extremely encouraging and exciting, and I want to talk to you today about ideas that I've been developing over quite a long period of time. And I'm not going to be able to cover everything that I've been doing recently, but you see, I've been working on two different tracks. One is related to quantum gravity, to conformal gravity as a quantum theory, and it's a fourth order theory, and there's a big issue about whether it's unitary. And Carl Bender and I, in a rather extensive collaboration, have been able to show that this theory, in fact, not just that it doesn't have a ghost, it never had one in the first place, and the argument that it did have was just plain wrong. And it turns out the reason is the theory is not a Hermitian theory. And you think of it as such because you just look at the Lagrangian, but you don't know the theory's Hermitian until you look at its asymptotic behavior. And when we did, we found out that it was totally not a regular quantum theory at all, but it's a consistent quantum theory. Now, I did talk about this the last time I visited here, though probably not everybody here was at that talk. I can't really get into this today, but I want you to know that I am fully aware of the unitarity problem, and I'm claiming in a series of papers that began with the FISREV letter in 2008 that Carl Bender and I have solved this problem. The other side of the coin is conformal gravity and the cosmological constant problem and its application to and its way of dealing with the dark matter problem. And through a series of papers, I've been able to show that you can dispense with dark matter, at least for galaxies, which is the only case that's so far been analyzed. But we've analyzed with my former student, James O'Brien, we've analyzed no less than 138 galaxies, and we fit the lot. So it's quite an accomplishment. Now, the theory itself, and what I'm really going to talk about today, is the zero-point problem, and it's understanding the zero-point energy density problem, which is the key to understanding quantum gravity and the key to understanding the cosmological constant problem. Now, let me begin with the very familiar Einstein equations. And now we have to ask, what kind of an equation is this? If two things are equal, then either this one is classical and that one is classical, or this one is quantum and that one is quantum. Take your pick. When Einstein wrote it down, of course, in 1916, it was presumed that everything here was completely classical. Quantum mechanics was discovered, and you can say, well, maybe gravity doesn't know about quantum mechanics. But we know that it does, because there are two very important quantum mechanical sources that play an important role in astrophysics. White dwarfs are stabilized by the Pauli pressure of the electrons in the white dwarf, and cosmology in the early universe is driven by the blackbody radiation, the cosmic microwave background, and both of these two are intrinsically quantum mechanical. Therefore, the sources that must appear in gravity must include quantum mechanical sources. But you can't have quantum equals classical, so what you do is you replace T by its expectation value. Now, when you write down an expectation value, it's a product of fields at the same point. This function is not finite. So you subtract off its infinite part, and standard gravity starts out with equation 3. Now, in doing this, you have done tremendous violation. One, it doesn't come from anywhere. It's just, we'll use this as a convenient starting point, but it's not derived from any fundamental theory. And even if you could get as far as 2, if you could derive that from a fundamental theory, then you're still faced with the fact you can't throw away a piece of the energy momentum tensor, because the whole point of gravity is that gravity couples to energy and not to energy difference. It's okay to throw away the 0 point if you're doing flat space physics, because in flat space physics you only measure energy difference. If we think about the famous double weld potential, then in the double weld potential, you measure that difference between the maximum and the minimum. It's the difference between 2 points of energy. But I could have written the double well down there. And so the question is, where is the zero of energy? And where the zero of energy is is basically the cosmological constant problem. So what do? We first of all throw away the 0-point energy. Now, what does this mean? We write down a set of oscillators, A dagger A plus a half h bar omega. We use the A dagger A to get the energy and the pressure of a black body, and we throw away the half h bar omega because we don't know what to do with it. What I'm going to show you today is that in throwing this out, you've thrown the baby out with the bathwater. Moreover, you've thrown out twins, because the half h bar omega doesn't just contribute to the density, it also contributes to the pressure. Because if the one-body modes above the vacuum have energy density and pressure, then the vacuum itself also has energy density and pressure. Therefore, there are two 0-point problems, the 0-point energy density and the 0-point pressure. But they both have the same sign, because for any massless perfect fluid, the pressure is always 1/3 of the density. Now, the cosmological constant has pressure equals to minus the energy density. Therefore, this energy density that you've thrown away is not the cosmological constant. It's a separate problem. There are two problems, the 0-point pressure problem and the 0-point energy density problem, and then subsequently there's the cosmological constant problem. Now, after you've done all this, if you insist on using this equation, and you've thrown away all of these 0-point problems, then what Sakharov showed is that for the vacuum, this number, the finite piece, is not necessarily 0. Lorentz covariance allows it to be proportional to the metric, allows it to be proportional to g mu nu, and therefore you can still have a cosmological constant term in this piece. And what we've discovered in years and years of hard work on this is that no one has figured out how to get rid of this. So it's something you would then, if you start there, you have to live with this term, and it seems there's no way to get rid of it. So what I'm going to argue today is, don't start here. And then we'll see how far we can get. Now, second point is, if I look at our familiar friend, the double well potential, then I already have a cosmological constant contribution, the energy of this vacuum, in flat space, in the absence of gravity. We just do flat space calculations. So gravity is going to get a source which contains the cosmological constant, which is coming from processes that don't involve gravity. So how is gravity supposed to solve this problem if gravity was not responsible for it? In order to try to solve this problem, I need to find a way to do much better in connecting gravity to matter. And the solution will be, don't expand in powers of g Newton, rather expand in powers of Planck's constant. Because then I can have classical equals classical, quantum equals quantum, and what I'll come up with later on is I'll actually tell you that in the theory of gravity I use, there is no h bar to the 0 term, that everything is going to be quantum mechanical, and what I'm going to argue is that the theory that we will need to solve these problems will have to be a theory in which gravity is quantum mechanical and matter is also quantum mechanical. Now, so, Einstein gravity, what can we say about it? Certain things we must agree on. We must agree that it's a metric theory. We introduce the Christoffel symbols, the geodesics, the Riemann tensor. All of that it must be in any theory of gravity. We also know that outside the sun, near the sun, the geometry is described by a Ricci flat metric. So no theory of gravity is going to get very far if it's not a metric theory of gravity and has, near the sun, Ricci flatness. So those are the ingredients. Now what's not written down here are the Einstein equations. All we need is this solution. We don't need the equations. We need the solution because it's the solution that we test in experiment. Now, so let me just show you what I could do if I, for the moment, without telling you why, I introduced the Weil tensor. And it was discovered by Weil. It's the Riemann tensor, the Ricci scalar, and the Ricci tensor, this curious combination. What Weil discovered was that if I make a local conformal transformation on the metric with the phase alpha of x, then the Riemann tensor, which is two derivatives of the metric, being a derivative of the Christoffel symbol, which itself is a derivative of the metric, then all of these terms pick up derivatives of alpha, but in this funny linear combination, the C, all the derivatives vanish. So the C does for a scale transformation what the Maxwell tensor does for a gauge transformation. So this is the, in fact, Weil introduced this to unify electromagnetism and gravity. That was his original objective, was to precisely make gravity into a gauge theory. If I take the C squared action, I can write it as Riemann squared plus Ricci squared plus Ricci scalar squared, but this funny Gauss-Bonnet term is a total divergence. I can get rid of Riemann squared, and so I can write the Weil piece as R mu nu minus a third R alpha alpha squared. And that's the term that we, in the end, are going to work with. If I take this as my action, do the variation with respect to the metric, I get an equation of motion, W mu nu equals T mu nu, and W mu nu is this god-awful thing. You do the functional variation, you have to integrate by parts over and over, and you eventually come out with this expression. This expression has a beautiful feature. If the Ricci tensor is 0, then W mu nu is 0. Therefore, Ricci flat is a vacuum solution to this conformal theory. So what we discover is Einstein is sufficient to give Schwarzschild and Newton, but is not necessary. There are other theories. Whether you like them or not, it doesn't matter. Einstein is not necessary for Schwarzschild. Consequently, the Einstein theory as it stands, if it is to be the theory of nature, you have to come up with a principle that would make it necessary. The equivalence principle only tells you that the gravitational action should be a general coordinate scalar, namely, it could be a Ricci scalar squared, Riemann squared, and so on. You never need to go to this particular action. And of course, if you do go to this particular action, then there's nothing to stop you from adding on a cosmological constant term. What got me interested in this theory was simply that, if this is an invariance of the universe, this action is unique, because I can't add in a cosmological constant because it violates the symmetry. Now, the symmetry gets rid of the cosmological constant, but it also throws out the Einstein term because G Newton violates the scale invariance too. But what I've shown you a moment ago, I can live without the Einstein-Hilbert term because I can still get the Schwarzschild solution in a totally different theory. I have to add conformal invariant matter. Yeah, but no, but matter is conformal invariant. The coupling of massless quarks to massless gluons is conformal invariant. So we're going to break the symmetry, yes. We don't have... Okay, let me just... Of course. Let me just point out the following. In this familiar theory, we take a scalar field and we let it go into the vacuum. And we always do this to break the SU2 cross U1. But the scalar field carries a dimension.
I was a different question. If you break the symmetry, then you have to include consequences of that breaking, and those consequences give you back the cosmological constant.
I know that. If I can get that far, I'll show you how, even after you break the symmetry, there's residual symmetry that will protect you. Remember, the Goldstone boson restores the symmetry. The Ward identities do not change. And we'll see that with the Ward identities are Ward identities, you take them in the normal vacuum or the spontaneously broken vacuum, and you're correct. We're going to precisely generate a cosmological constant when we break the symmetry, but we'll have enough residual symmetry to get rid of it.
But we're talking about local symmetry here, right?
This is, yes, exactly.
So therefore local symmetry is not a Goldstone boson generator.
No, I just meant to show you the exact... We know that when we do chiral symmetry breaking, we do get a Goldstone boson, and it restores the symmetry because the Ward identities don't change their functional form. The same thing is going to be true here. It's not going to be realized in the Goldstone mode, but that's not the point. I mean, that wasn't the point I was trying to make.
So another question.
Yeah,
I don't know if you are still including Einstein-Hilbert or not.
No, I'm not.
Okay, so then we measure much more beyond just short.
I know all this.
Yeah.
I'm fully aware of this.
So do you recall, let's say, Hals-Taylor, pulsar
Not, there are many. Okay. Okay. I'm going to tell you what I've done. I can also tell you what I haven't done, and I'm fully aware I've not yet calculated the binary pulsar decay. I've shown that it occurs because this is still a covariant theory of gravity which has retardation. So it must occur. Will I get the right number? The answer is I don't know, and I'm aware of that. I've got issues related to lensing, which I'm still dealing with. But I want to deal with this theory. What I'm trying to say today is the following. I'm developing the theory from fundamental principles. Then we'll go ahead and apply it and see if it works. If you, and I can tell you what I've done. I'm going to show you, if we have the time, what's happened with the rotation curves, which is the only thing that I've worked out in any detail, and there the success is rather good.
Yeah, I just wanted to comment on what Gregory said. Almost all the precedent tests of gravity are tests of vacuum gravity.
No,
so it's not just Schwarzschild. I mean, if you have that R mu equal to 0 equation,
yeah.
then you essentially satisfy almost all precision tests.
Yeah, the statement is the correct statement is the following. Okay, no.
Get the number.
No, but
the GR gives you the right number. Then how come the theory, which is dramatically different from GR?
No, but that's also a theory of vacuum gravity.
No. But both of you. There are two statements that are important. One, any vacuum solution to Einstein is a vacuum solution to conformal. Two, on static gravity, this theory recovers solar system Schwarzschild solution on solar system distance scales. The binary pulsar is on solar system scales, not on galactic scales. So the only question you're asking is the only question you're asking is whether the non-static recovers. I understand the question. I can only tell you what well, let me put it this way. I'm going to give you. I'm going to give you a complete theory of quantum gravity for which I have applications to data. The only competitor is something called string theory, for which there are as yet no applications. So I'm ahead, which is all I have to pick. Now, so Einstein is sufficient to give Schwarzschild, but not Newton. Now, if we take the Einstein theory and we continue it beyond the solar system, we find the following. One, when we go to galaxies and larger, we need dark matter. When we go to cosmology, we have the cosmological constant problem. When we go to strong gravity, we have the singularity problem. And when we go far off the mass shell, we have the renormalization problem. Now, all of those problems are severe. None of them have been solved in a way that has given rise to testable predictions. And all of them are coming from taking one action and continuing it beyond the domain in which it was established. I'm going to argue that maybe we can dispense with this action and use this one, and then if I'm able to solve any of those problems, I will have to be able, I would be able to solve all of them because I'm telling you that they have a common disease, and therefore I'm going to try to offer you a common solution. Okay. Now, please, absolutely. Well, I've done the linear perturbation here. So far, I've only the unitarity problem is the question of whether flat space-time is stable, and I've shown that that's the work of Bender, and I've shown that it is. I haven't done anything beyond that. Okay, but there's a reason I haven't done anything. I mean, it's because because in this theory there's no classical gravity. The Schwarzschild solution is output to the quantum mechanics and not input. So there's no meaning to the question, take a classical solution and ask if it's classically stable. In this theory, the classical solutions are a consequence of quantum mechanics. So the whole discussion is going to change. Okay, now, so let me try to argue why conformal gravity is natural. If we introduce a gauge invariant, psi goes to e to the I beta of x psi, we introduce a gauge field which picks up a d mu beta, and I d mu plus a mu is the familiar gauge invariant action. Suppose I want to take psi and give it a Lorentz transformation, but make it a local Lorentz transformation. Then the d mu hits the w mu nu of x. This term is no longer locally Lorentz invariant. Fock's solution to this is introduce a spin connection. The spin connection is constructed from the vierbeins. It's a rather complicated object, but then you come up with an action for gravity, a coupling of matter to gravity, which is now locally Lorentz invariant, as well, of course, as being coordinate invariant. However, you get something for free. And the something that you're getting for free is this action is also locally conformal invariant. You didn't ask for it to be, you only asked for it to be locally Lorentz invariant, but it turns out to be locally conformal invariant under a local phase on G mu and a local phase on psi, then you'll find that this action is a complete invariant. So if I write down now the coupling of a matter field psi to gravity, gamma mu, and to A mu, then this action has a double invariance, e to the I beta minus 3 over 2 alpha. It is both locally gauge invariant and locally scale invariant, all in one go. And all I'm doing is I'm saying, instead of taking the phase to be pure imaginary, let's let the phase have a real piece as well. That's the only difference, and that's how I hope to unify gravity and electromagnetism. Now, when you look at the light cone, of course, has 4 invariances, the flat space light cone, 4 translations and 6 rotations, but it also has a dilatation. If you let x go to lambda x, then if this is 0, it remains 0, and it has these rather peculiar 4 conformal transformations. So the light cone admits of 15 invariances and not just 10. The generators are p mu, id mu, m mu nu, and so on. D is x dot grad, c is x mu, x dot grad minus x squared d mu nu. When you calculate the algebra, you find that these generators close on an algebra, and that algebra is SO42, because SO42 has 15 generators. And that's the conformal group, and therefore the light cone is conformal invariant. So in the absence of mass, all particles move on the light cone. In the absence of mass, therefore, you have conformal symmetry. Now, if you look at the Dirac algebra, you introduce the Dirac matrices. Gamma mu is 4, 6 gamma mu gamma nu, a gamma 5 is 1, and another 4 gamma mu gamma 5. You find that the 15 Dirac matrices close on the same algebra. And the reason is SU22, which is that algebra, is the covering group of SO42, the same way SU3 is the covering group of SO3. What that means is that the 4-component fermion, the 4-component fermion of the 4-dimensional Dirac matrices, is the fundamental representation of the conformal group. Now, why is this so important? Under Lorentz alone, the fermion is reducible. It's d1/2 0 plus d0 1/2. It's reducible under the Lorentz group. This is very bizarre. Why should the fundamental fermions be reducible under the most important group there is, the Lorentz group? But what? The Dirac fermion is reducible. Yes, the Weil there are irreducible. The best you can do with the Lorentz group is have 2-dimensional irreducible, and then you hope that for every 2-dimensional irreducible, some other 2-dimensional irreducible will come along and combine with it and make a mass. But there's nothing in Lorentz group that tells you that should happen. However, in the conformal group, it tells you it must happen, because now the fermions are irreducible under the Lorentz group, under the conformal group, and therefore, if there are left-handed neutrinos, then right-handed neutrinos must exist, and therefore the strong and weak interaction should be chiral. So chirality is natural once you have the conformal group. Now, I have been very worried for many years, why should the fundamental 4-component fermions that we use every day, why should they be reducible under a group? If they're the building blocks, surely they, above all, should be irreducible. And the answer is they are irreducible under the full invariance of the light cone. Now, that's the algebra. Now let's go to the geometry. Flat space-time admits of 10 killing vectors. If we introduce k mu is a mu plus b mu nu x mu, where b mu nu is antisymmetric, so there are 4 a's and 6 b's, then d mu k nu plus d nu k mu is 0. Those are the 10 Killing vectors because flat space-time is maximally symmetric. However, flat space-time also admits of another 5 operators, lambda x mu and c mu x squared, and now d mu k nu plus d nu k mu is not 0, but it's proportional to eta mu nu, and those are called conformal Killing vectors, and therefore flat space-time actually has 15 Killing vectors, 10 regular ones and 5 conformal, and they of course form the conformal group. Now, let me now do the following. Let me make the whole 15 local. When I make the whole 15 local, make the A local, that's coordinate invariance. Make the B local, that's local Lorentz invariance. Make the lambda and the C local, that's conformal invariance. So let me just say, whatever are the Killing vectors, let me make them local symmetries. This is what we do all the time in QCD. Now I've got my action, psi bar gamma mu, id mu plus I gamma mu plus A mu, psi. That's the only one that the fermions, which are now, remember, the fundamental of the group, therefore they have to appear. That's the one, that term needs to be there. But what about the gravity sector action? That's not fixed yet. However, 't Hooft gave an answer to that. This is quadratic in the fermion field, bilinear. Therefore, you can do the path integral and generate an effective action. And when you do this path integral, you get what you always get, the trace of the log of the inverse propagator. And when you expand it out, you regularize it using dimensional regularization. You find a term that goes like r mu nu squared minus a third r alpha squared, and a second term that goes like f mu nu, f mu nu. So what you discover is, when you do this integral, you generate none other than our friend, the Weyl action. You also generate the Maxwell action. What you do not generate is the Einstein-Hilbert action. So what this is telling us is that if I start out with this action, psi bar, gamma mu, id mu, plus I gamma mu, A mu plus A mu psi, which everybody does, that's the standard action. The locally coordinate invariant gauge invariant action, and I just do the fermion path integral, I'm going to generate the c squared term, and it will come alongside the f squared term because they go hand in hand. Therefore, you have to live with the c squared term. It's going to appear in any theory of gravity, whether or not you like it. It's not at your discretion. Once you've committed to this action, which we all do commit to, then a quick Gaussian integral over the Grassmann psi and psi bar generates the conformal action at the same time as the Maxwell action. So it's not as though I'm using it because I want to be nasty. It's there, and you have to find a way to live with it. If it's true that this is not unitary, then you're saying that this theory that we know and love is not unitary either, but fortunately, you can stay with this theory because Carl Bender and I have shown that, in fact, this theory is unitary. So what we see is that the Weyl action is on the same footing as the Maxwell action. Yes, sir? Yes, of course.
So if it's massive, that violates symmetry.
No, I'm going to generate the mass dynamically. The same way you do, called the Higgs mechanism. There's no electron mass in 3 × 2 × 1 in the Lagrangian.
There must be somewhere the mass parameter. Whether you generate with a Higgs mechanism or whatever mechanism, there is a dimensionful parameter.
Yes, it's going to come from the vacuum.
So that dimensionful parameter violates the symmetry.
Of course, that's
so then, as a result, you will generate Einstein-Hilbert
Memento. That is called Coleman-Weinberg. Yes, I fully agree with you. That's what I'm going to do. I did it 30 years ago, but without reference to gravity. Now I'm going to do it with gravity. But yes, of course, that's absolutely correct. Now, but let us just follow Gregory's question. Let's suppose that I had started with a mass term as well. Now, where would that mass term come from? It's going to come from some mean field approximation to some kind of generalized non-Boolean Lassiniel. But for the moment, let me just assume there's a mass term. Then I can do the path integral now with the mass term. It just gets the same trace of the log, but with the mass term. And then you generate, in addition to these, a minus m to the 4, a 6m² r alpha alpha, and a kinetic energy term for the m. Now, what have I got here? This is the Higgs potential, only the tachyon is the Ricci scalar. So in a background geometry where the Ricci scalar is non-zero, I've generated dynamically a double well potential, and then I can find solutions to the equations of motion in which m is self-consistently non-zero. So that's what I'm going to do. So the message here is that the double well potential doesn't have to be minus m squared phi squared. It can be m squared times the Ricci scalar, because the kinetic energy is not locally conformal invariant. It's only when you add on this sixth m squared r alpha alpha term that you then have the conformal invariance restored. Finally, I can give m a gauge index, and that's what I did and Noguchi and Sugawara did, I'm afraid, an awful long time ago, and then this term gets replaced by d mu plus ia mu m, d mu minus ia mu m. So what have I obtained? I've obtained the standard gravity sector, what we usually call the Higgs sector. I've derived it dynamically, starting from this action for the fermion with some mass generated by some analog of a 4-Fermi interaction in the standard Nambu-Jonas linear way. And what do I come up with? I come up with a mean field action, and what I'm telling you, what this is called is, this is the Ginzburg-Landau action of conformal gravity. Okay. So we now see, we're starting to get into the issue of conformal symmetry breaking. We can see that it's doing some very, very simple things, not a single one of which is controversial. I just start out with the action that everybody uses. I generate a mass by a dynamical mechanism that everybody uses. I read off what's the effective action, and the effective action is the Ginzburg-Landau action. And the only difference between what I've done and what Mr. Higgs did, Mr. Higgs made this a fundamental field. And the only thing I'm doing that's different, I'm saying, is no, it's induced by symmetry breaking. It's a fermion bilinear. Otherwise, it's exactly the same. Yes, sir? I'm sorry?
Is the mass then going to be set by the Ricci scalar? Is it
Yes. You read this in two ways. The Ricci scalar is non-zero, gives the mass a value. The mass non-zero generates a Ricci scalar term. So the two go together, and that's called self-consistent, and I have to show that the theory has self-consistent solutions, which I've already done. Yes. Yes.
You mentioned the word tachyon.
Yes. Yes.
Do you are you saying that you automatically find tachyon field coming out of zero?
No. What I said was I automatically find a potential which has a quadratic term and a quartic term and a quadratic term. Okay. Then, depending on the background geometry, whether the Ricci scalar is positive or negative, whether you're in a background de Sitter or anti-de Sitter, will determine whether this is a single well or a double well. Yes. Yes. Yes, sir.
When you do Higgs for the usual potential beta phi,
yes,
you all within 3 lines you produce a vacuum energy which is huge.
Yes.
What happens here?
Well, that's the point of the talk.
Huh?
That's the point of my talk. So first of all, I want to show you how this happens in principle. I want to show you that I'm not doing anything unusual, and I'm getting down to something that we know and love. So what I'll later on show you is I need to go beyond this log divergence in order to solve a complete theory, and that's what I'll do. That's what I'll try to show you in the next few steps. Now, second piece of argument, which is totally from a different source, is a recent discussion by Tahouf. What he said is the following: start with the Ricci scalar, Einstein-Hilbert action, and just make a scale transformation on the metric. Just define it as omega squared times g hat. Then you can show that this action gets written in terms of the Ricci scalar calculated with g hat, and the metric calculated with g hat, the determinant of the metric with g hat, times an omega, which is exactly the scale factor. That's just a mathematical identity. He now says, let's do the path integral over omega as a dynamical degree of freedom. This is somewhat similar to what's called unimodulogram. But the point is we can do the integral. It's quadratic in omega. It therefore is going to be the trace of the log of its inverse propagator. And when you regularize that out, what you get is r hat mu minus the third r alpha squared. In other words, you start with Einstein gravity, integrate over the scale factor in the metric, and you generate the conformal gravity action. Now, none of this is controversial. So it is telling you that you're going to get this term, and therefore you're going to have to learn how to live with it. So we have two separate ways of showing that this term must play some role in physics. One is integrate the fermions, and the other is start with the Einstein-Hilbert action and integrate over the determinant of the metric.
So,
Yes?
so 2 shows that C is infinite.
No, C is this C. It's the same one. It's that particular C. Tuff showed that it's that particular C. Yes, I said it. I have to regularize it. But that's okay. Log divergences have appeared in physics for a long, long time. Getting a log divergence is not bad news. Getting something that might not be unitary is bad news. And so the question is, if this theory as it stands is unitary, and if this theory is supposedly unitary, then this integration cannot destroy unitarity. Therefore, there must be a way to reinterpret this as a unitary theory. And that's what Carl Bender and I have done. Now, so Huff shows that you can start with Einstein and you generate conformal, and Maldacena very recently said, let's start from conformal and let's try to generate Einstein. So what we're seeing is that these theories are tied up once you start thinking about gravity. Now,
So, Flip, I mean, I
Yeah.
just want to comment. This last argument, right here, this is not a physical argument. You cannot, I mean, this omega is not really a physical degree of freedom that you want to integrate out.
I thought that all the components of the metric are physical.
No, you don't have any scalar graviton.
I never mentioned scalar graviton.
Well, that is the scalar.
I did not mention scalar gravitons. But let me try to answer your question. Whoops. Let me try to answer your
This
question.
is just a mathematical procedure.
Okay. If you take in standard gravity, you linearize around flat space-time, you go down from 10 degrees of freedom to 6. Those 6 is a 5-component spin 2 and a 1-component spin 0. That 1-component spin 0 is the thing that gives you Newton's law. That's a scalar.
Yes, but it's not the dynamical scalar.
Of course it is. It's the thing that produces Newton's law.
Well,
Because the tensor is traceless.
You don't quantize Newtonian potential.
I quantize the remaining 6 degrees of freedom. All 6 of them. I don't have the freedom to quantize less than...
Two physical helicity.
Oh, that's on shell. On shell there's 2,
Yeah.
but off shell there's 6.
So that's what...
No. You have to you don't quantize on shell. You quantize off shell. Anyway, this is a completely normal prescription. There's nothing wrong with it. I've just done the path integral. I've reorganized the integration in a different form.
Well, I mean, you're integrating now something that's not physical, so I'm not sure what that means.
I don't quite understand the question. Anyway.
Well, what Yesha is asking is that there is in your Lagrangian 26, there is a gauge transformation.
Yes.
So by that gauge transformation, you can put omega equal to 0. That's a choice of gauge.
No, this is a gauge invariant.
Omega equals 1.
Both of these expressions are gauge invariant.
No, full expression is gauge invariant.
Yes.
And then there is a gauge symmetry of that Lagrangian,
Yes.
which is what you wrote up there, which
Yes.
is the transforming of G with omega and then probably omega also transformed somehow.
Yes.
So by that transformation, then can fix a gauge.
Yes.
That's an additional gauge transformation on top of diffeomorphisms.
This is what we're doing. Basically, you read this the other way around. We're using the Einstein-Hilbert term as a gauge-fixing term for the conformal theory.
Oh, then his question still applies.
Yes.
How come something that you can gauge away
No,
gives you anything dynamic, anything new?
Are you worried about integrating over an infinite number of the omegas?
Well, that mode is just gauge mode. It's not a physical mode. So which means that that theory...
If it's a gauge thing, it doesn't make any difference. And the theory is gauge invariant. It makes no difference what the value is. Therefore, you can average over an infinite number of them. You get an infinite volume you could divide that by, and that's that.
No, but then that means that 26 has to be equivalent to just GR.
Okay. This is a metric.
Right?
This is a metric which is written down. There's 9 of these, and one of those is the 10. There's still 4 coordinate invariances. That's all, and I have them all.
Let me ask you a different question.
Yes.
I'm sorry to
Yes.
take time, but if you never introduced omega
Yes.
and did some loop calculation
Yes.
just in GR,
Yes.
would you still get correction which is 27?
Okay. Let me try to. Okay. The standard argument that Einstein gravity is not renormalizable is that as soon as you do loops, you uncover quartic terms.
Yeah,
And
but
when
you should get exactly that term. Do you get that?
You don't get that particular term. It depends what way you do the integration, I think. But nonetheless, you're always going to finish up with some quartic terms. Now, the argument, by the way, is not that r mu nu squared minus a third r alpha squared is not unitary. The argument is that any quadratic term in the geometry is not unitary. Therefore, you're always going to, as soon as you do perturbation theory any way you want, you're going to introduce a term that's quadratic in the Riemann tensor. Now, then you do 2 loops and you get cubic in the Riemann tensor. 3 loops, quartic in the Riemann tensor, and so on. You're going to get an infinite series, and the only reason that Einstein gravity is not renormalizable is it doesn't terminate. Every time you go to another order, you get to have another order in the Riemann tensor. However, what this is telling you is you're always going to have to deal with these higher order terms. You can't prevent them, no matter how you organize it.
That you understand very well. I mean, his question was different,
Yes.
which is that if that term is right, what you are writing.
Well, this is just a mathematical
So then you
reorganization.
should be able to get that term just from GR without any reference to that omega. Because the 26 is identically GR whether you write with omega or without omega.
Yeah.
So that was his question. So
No. In GR, there are 10 jihads. In this way of writing it, there are only 9 jihads. This is slightly different. This is only a function of 9 degrees of freedom of the metric. 1 has already been integrated out. It's not quite GR.
In the original paper by Tuch and Veltman that first established that gravity is not renormalizable, you found these quartic terms as the additional terms, and those are the ones that cause trouble. You don't have to go through this route to see this.
Yeah,
This has been known for years.
You're always going to get terms that no matter how you do it. No. What is asked is you have to get the conformal combination, and that's the only question. But you certainly have to get certainly have to get the terms that are quadratic in the metric. Okay. Now let me skip. I'm going to go a little bit quicker.
Philip, can I just add one point about the two?
Yes.
And so 2 metrics that are conformally related are not diffeomorphic. I mean, like in Cauchy space and
they're not, of course.
So I mean, so he is integrating over physical.
Yeah, what I'm saying is that theory with omega is identical to GR.
Or maybe this is for Nick.
It's not quite identical to GR because this only has 9 degrees of freedom, not 10.
So you can always find a diffeomorphism. This
is not a diffeomorphism.
It is not. That is not a diffeomorphism. But
Yes. And it's saying, and also, all I've done is I've made a conformal transformation on an action which is not conformal invariant, and therefore I don't get back the same thing. That's all I've done.
Yeah, so like flat effort.
It's what you usually call going from the Einstein frame to the Jordan frame. That's what it's usually called.
The flat effort W metric.
If you impose extra symmetries, then it makes it different. But my point is really a separate point. My point is that that's not a physical degree of freedom. We know that the physical degrees of freedom of metric are classless transverse ones. And those are the ones that
there are 6 physical degrees.
The other ones can be.
No. The gravitational field has 6 observable degrees of freedom. Free plane waves on shell only have 2. But the other 4 appear off-shell in Feynman diagrams. You have to carry in, it's just like QCD, you have to carry the longitudinal photon in the virtual loops. It just doesn't go on shell.
Yeah, but we don't call them. Okay,
That's a matter of definition. It plays a role in the theory. And this familiar graph,
this point is independent of that.
this familiar graph, which it just gives you the Gn1 and 2 over R, you're just taking the source at rest. When the source is at rest, its energy momentum tensor is not traceless. But the 6 degrees of freedom of the graviton are one scalar and a traceless tensor. If you go on shell, you finish up with just helicity 2 and helicity minus 2, but they're both traceless. But a traceless graviton can't couple to give you Newton's law. So if you want to say, I only keep the 2 degrees of freedom, you won't even get Newton's law of gravity.
It says something else.
Yes, so the question of what constitutes a physical degree of freedom is a totally different question. Anyway, let me stop at this. Let's try to complete the talk.
I'm trying to understand what we're arguing about. This is totally
I think it's a good idea to move on because I think
Okay, that's
why are we arguing about this?
No. Let's resolve it later. I'll never finish. Okay, now I wanted to talk about quantization of gravity through coupling. Let's see, how does gravity get quantized? Why is it different than anybody else? For a fermion field, I introduced just flat space-time, equation of motion, Dirac equation, canonically quantize, psi dagger to delta function, expand psi in a complete basis of solutions to the wave equations, and I discovered that the B's and the B daggers anti-commute, the D's and the D daggers, that give me an anti-commutator like this. So now I calculate the vacuum expectation value for this theory of the energy momentum tensor associated with this action, do the variation with respect to the metric, go back to flat, that's what it is. Vacuum I psi bar gamma mu d mu psi, a vacuum, and when you put in all the modes, it's the integral d3k over k0, k mu k nu. K is it's massless, so k is traceless, and therefore the trace of the energy momentum tensor is 0. Therefore there's a pressure and there's an energy density, and the pressure is 1/3 of the energy density, but both of them are infinite. Now, evaluating this quantity out, I find I've got a 0-point pressure, which is infinite, and a 0-point energy density, which is infinite. A 0-point pressure and a 0-point energy density. Now, but I don't care when I quantize a field in flat space, because I can throw these away. The 0 of energy is not observable. It only becomes observable if I couple to gravity. So as long as I'm doing flat space quantization, I can be completely canonical, and I can say, well, T mu nu has a non-zero value, but I don't care. It doesn't affect the quantization. It doesn't affect the interactions that I then construct through the Feynman series. So can we do the same thing for gravity? So now we go to gravity. Now what we find is we'll define T mu nu of gravity to be the variation of the gravitational action with respect to the metric, and therefore the equation of motion is T mu gravity equals 0. We've been discussing a lot. When we linearize Einstein gravity around flat space-time, the propagating degrees of freedom obey T mu gravity, first order, is 0. Now, so let's now go to conformal gravity, expand around flat space-time, calculate the first order term. I chose a particular gauge. It turns out I introduced the traceless piece of K, and in that particular gauge, the equation just becomes box squared. K mu nu is T mu nu, and therefore if it's 0, K mu nu is 0, and therefore I can expand K as an A plus an n dot xb. I have the usual plane wave, and then I've got this funny term because it's a fourth order theory. The reason for this second term is the box of it just gives me that one, and therefore the box squared of this is 0, and therefore it's the other solution. So I now make a canonical quantization in terms of the A's and the B's, and I write down all of the possible canonical commutators, and I just put in here for the moment a factor z of k because I don't yet know what it is. So now I calculate the second order term, and I get this term is quadratic in K. I just keep on expanding. I calculate the second order contribution to T mu gravity, and I get that it is non-zero. On the contrary, that's the 0-point energy of gravity. However, now we've got a problem. We are trying to maintain an equation of motion. But the equation of motion for gravity is not consistent with the quantization of gravity. The equation of motion for matter is the Dirac equation. It is consistent with the quantization of the Dirac field. The energy momentum tensor might be non-zero, but that's not its equation of motion. Therefore, that's not the thing you look at in canonical quantization. However, now, the vanishing of T mu nu gravity, which would just be the Einstein tensor or the Weil tensor, whatever you use, that one is the equation of motion, and it gets destroyed by quantization. Therefore, canonical quantization of gravity does not work. So what can you do? What you can do is you look at this and you say, wow, that's exactly like the piece that we got for the fermion. So therefore, suppose I now take the two theories at once. I take gravity plus matter. Then the equation of motion, which is usually called the Einstein equation, says that the T mu nu of the universe, T mu gravity plus T mu matter, is 0. That's what it says. Now, what that means is T mu nu of gravity, we got a positive contribution from quantizing the Weil gravity. We get a negative contribution from quantizing the fermion. Those two cancel, and therefore Z is equal to 1. So what we discover is that because gravity is coupled to a source that gravitates, gravity cannot be quantized on its own. Moreover, if the source is quantum mechanical, then gravity has to be quantum mechanical too, and both of these terms are expanded as a power series in h bar and not as a power series in g Newton. And when I do that, this is a constraint, that's the stationarity condition, and that demands that the sum of these two vanish. This is a little bit like supersymmetry because this is a boson, this is a fermion, and that one's a boson. Now, you can immediately say, well, that's very nice, but suppose I take the source to be more complicated. Suppose I take m massless gauge bosons and n massless two-component spinors. Then this 0-point energy gets to be n minus m over 2, and therefore Z has to be n minus m over 2. So let's state that again only very strongly. I introduce a Z from the canonical, from a candidate canonical quantization in the standard way. Equal time commutator is a delta function times a Z. The Z is then fixed by the matter content. Change the matter content, and you change Z. So the wave function normalization constant of the graviton is not specifiable on its own. It can only be specified by its coupling. So gravity doesn't ever get quantized on its own. It gets quantized by its coupling to matter, and then if matter is quantized, gravity will be quantized too. But this is a mathematical identity. Therefore, it says divergent pieces cancel, finite pieces cancel. Finite piece, bring that onto the other side. That's the standard equation of motion that you use to fit data. So what is happening here is that the infinite pieces are taking care of each other, leaving you a finite equation which you can then use to fit data. Now, and now you notice this is totally different to Einstein, because what we were doing for Einstein was saying the classical Einstein tensor is a matrix element of T mu nu. Now we're saying no. The quantum gravity piece is equal to the quantum gravity piece of matter, and therefore the infinite pieces cancel separately, and the finite pieces cancel separately, because that's the stationarity condition, the condition that stationarity with respect to the metric is 0. Okay. In good Schwinger language. Now, we discover also that gravity is quantized by virtue of its coupling to matter. Now, I'll jump ahead, and I want to say that what I'm going to show you later is that when I change the vacuum and make the fermion massive, well, when I make the fermion massive, all these energies are going to readjust because E becomes the square root of k squared plus m squared, but everybody is going to readjust so that this remain true, because that's an operator identity, it's a ward identity, it's true in the normal vacuum, it's true in the broken vacuum. But then these terms will readjust and Z will organize itself automatically to still make sure that the cancellation takes place. So the answer to John's question of a moment ago is when you change the vacuum, you will have to change the way that the gravitational field is quantized. It will do it in such a way that this remains a mathematical identity, and then you will discover that the cosmological constant that's induced will be divergent too, and this will continue to hold. Yes?
So, this brings me to the next question.
Yes?
Why doesn't this work for the standard Higgs model?
What is the standard hit? You mean the Mexican hat? Because the Mexican hat violates conformal invariance. I don't have the conformal constraint with the Mexican hat. If you put in the minus mu squared phi squared as a fundamental term, then mu squared has a dimension. And that's the tachyon. I have to induce the double well potential by dynamics. I can't start out with it. But let me rephrase John's statement. In the standard SU3 cross SU2 cross U1, the entire gauge sector, fermion sector, is conformal invariant because all coupling constants are dimensionless and all masses are zero. The only place in the standard model where you break the conformal invariance is in the double well potential, the wrong sign, mu squared phi squared. If I can induce that by dynamics, then I can have a theory of 3 cross 2 cross 1, which is completely conformal invariant, but then spontaneously broken by dynamical Higgs mechanism and not by a fundamental Higgs mechanism. But yes. However, what you can't do in standard gravity is do this cancellation, because standard gravity, this equation, does not survive radiative corrections. But if I'm in a renormalizable theory, which conformal gravity is, then this equation will survive radiative corrections and becomes an operator identity for the renormalized fields. Okay, now, let us go back a second and ask, we now believe that all mass and length scales come from symmetry breaking. None are present in the fundamental interaction, provided I can get rid of this mu squared phi squared term. So, suppose the mu squared phi squared term is not present in the fundamental theory. Now, that means that there are no scales in 3 cross 2 cross 1. All scales come from symmetry breaking, from vacuum breaking, and therefore, but vacuum breaking itself is quantum mechanical, therefore all scales come from quantum mechanics. But the scales of quantum mechanics, the masses of particles, are the things that you use to give curvature. Curvature, you will only have Minkowski if you write down a non-trivial Riemann tensor, then it has to be a function of the coordinates, but it has to be a dimensionless function of the coordinates, therefore you need masses. So the Schwarzschild metric is the Schwarzschild radius divided by the distance from the point of observation. But if all scales come from quantum mechanics, then all curvature comes from quantum mechanics, and therefore gravity must be intrinsically quantum mechanical. So what I'm arguing is that once we accept the conformal invariance notion that conformal invariance is a property of the Lagrangian, it's broken in the vacuum only, and not broken intrinsically, which is what the Higgs term, the tachyon, might do, then all mass is dynamical, and therefore all curvature is dynamical.
Now, that has a remarkable consequence. It says classical gravity doesn't exist. Classical gravity is induced when you take this equation and you take matrix elements not in the vacuum, but in coherent states of many gravitons, because that's what you do in electrodynamics. You take QED. To go to classical electrodynamics, you take its matrix elements in coherent states of an indefinite number of photons. We can do exactly the same thing for gravity if I have a renormalizable theory of gravity, which is what I have. So I can start out with quantum gravity and produce macroscopic classical gravity, not by taking h bar to 0, because h bar never goes to 0. It's non-zero in the real world. Never goes to 0. It's that you put in states with a large number of degrees of freedom. So classical limit does not mean h bar goes to 0. It means states become macroscopic. Now, when you do that, you will discover that the equations of motion, that the h bar dependent terms may drop out, but they really don't drop out, because remember, the white dwarf got its mass by Pauli degeneracy, and the Chandrasekhar mass that it gets depends on Planck's constant. So when you do classical gravity with a white dwarf, there's an h bar hidden inside the m. You may not be thinking of quantum mechanics, but there's quantum mechanics buried in the mass of the white dwarf that you might want to consider in a classical gravity calculation. So quantum mechanics is never switched off. Space-time is therefore intrinsically quantum mechanical. Now, the big bonus of this, as far as I can see, is it means not just that there are no classical intrinsic gravity, there can't be any intrinsic black holes. Therefore, the challenge that people are dealing with, how do we start with a classical black hole and quantize it? That challenge never has to be met, because there are no classical black holes in this theory. If there are to be black holes as output, it's a consequence of quantum mechanics, not an input that quantum mechanics has to deal with. But it's very likely, and I can't swear to this, that when you do this, you may never generate any black holes quantum mechanically, because the uncertainty principle is always going to smear singularities out. So it's quite possible that this theory may finish up with no singularities. There's certainly none in the classical theory, because the classical theory is flat, and it may be that the quantum theory might not give it either. So that's the basic notion, and what conformal gravity buys you is it solves the 0-point problem. Now, the next question is, what happens to the... Oh, okay, so, well, then you have to tell all these people not to ask me questions. That makes it very hard. Okay, that's fine. It's not a problem. What I want to do is I won't discuss anything about what happens when you shift to the new vacuum and how the z of k reorganizes to cancel the cosmological constant that's induced, but it's guaranteed to happen because I have the identity, T mu universe is 0. What I want to do finally, just very quickly, just to give you some sense of how the theory works, this upper curve, the upper curve is the fit to the accelerating universe data using the conformal theory. The lower curve is omega m is 0.3, omega lambda is 0.7. The only thing is the upper curve did not require any fine-tuning. So it fits the accelerating universe data without fine-tuning. You push the data out to higher redshift. The conformal theory will give continuing acceleration. The standard theory gives deceleration. And so by a redshift of 3, you should already be able to see a difference between conformal gravity and standard gravity if we can get out to that high redshift. Now, the dark matter problem, very quickly. The theory, I'm not going to do anything. I won't even say the words. When I'm through, I finish up with this formula. I finish up with a local piece. The local piece involves a linear potential and a 1 over r, because instead of solving the second order Poisson, I solve the fourth order Poisson. Then I integrate this over the galaxy. So that's the interior piece. And then once I also have a contribution from the outside. If you ask me later, I'll tell you why. But just allow me to tell you, here's a formula. Everything is fixed. Gamma is a number. Kappa is a pure number. Beta star is a standard Schwarzschild radius of the Sun. Gamma star is the the conformal gravity radius of the Sun. N star is the number of stars. The only degree of freedom is N star, which is the mass to light ratio of the visible material. And now I take this theory, and I'm going to tell you that I can use this equation with only the N star as the only variable and fit 138 galaxies without any dark matter. So let me just show you the fits. So this is the first 18, and the thick line is the fit. Then there's another 15. Then there's another 15. Then there are 20 low surface brightness galaxies. Then there's another 21 low surface brightness galaxies. Then there's a lot of then there's a huge number of other galaxies. Then finally, we'll go to 24 dwarf galaxies, and then the other part of the packet. And then finally, these last 6 galaxies, I'll only highlight them because these are the same galaxies that Dr. Kapling had talked about on Tuesday. And what you can see is that conformal gravity has no trouble with these galaxies. What's really interesting is these are dwarfs, so they don't go out very far. This only goes out to 3 kiloparsecs. The luminous piece is almost non-existent because the low surface brightness. Everything is in those linear terms, those gamma terms, and that's the fit. And I don't have any of the FNW problems. This theory can just as easily do high surface brightness galaxies such as these, and low surface brightness galaxies and dwarfs such as these. So I wanted to show you this, and I want you to remember only that the NFW treatment of these galaxies requires 2 parameters per halo, and therefore has 276 more parameters than this theory. Finally, I will close with a philosophical comment, and the philosophical comment is the following. This is summary. At the beginning of the 20th century, studies of black-body radiation on microscopic scales led to a paradigm shift in physics. Today, we're in the 21st century. We're again studying black-body radiation, but now on macroscopic cosmological scales, and we're running into the dark energy problem, the cosmological constant problem, and so on. And maybe they may be indicating time for a paradigm shift again. So I'm offering you this as a possible theory. Clearly, there's a long way to go, but nonetheless, I believe that there's a coherent framework which can be explored and give a potential replacement to the standard theory. And I'm arguing is that what we're seeing in the data might be pushing us in that direction. Thank you very much. Yes, later.
There was a lot of stuff at the end there. So the first thing you mentioned about fitting the data was the supernovae.
Was what?
The supernovae, you have these plots.
Yeah, yes.
So just to be clear about what you do there, you're saying you take the omega matter that is measured by cosmologists.
No.
You put that into your analog of the Friedman equations. Solve them.
Okay. Well, okay. Very quickly. This is stuff I published quite a long time ago. In the conformal theory, something remarkable happens. The equation of motion is W mu nu equals T mu nu. But W mu nu is proportional to the Weyl tensor, and the Weyl tensor vanishes. Therefore, in the conformal theory, the equation of motion for cosmology is T mu nu equals 0. Now, that's why the conformal theory knows where the zero of energy is. That's how I'm able to solve the cosmological constant problem. But that condition is non-trivial because there's positive energy density in matter, there's positive energy density in radiation. Where does the negative come from? It comes from curvature, the curvature of the gravitational field. You're forced into K negative. When you take the K negative theory and you go ahead and you solve that equation, you get those fits. In those fits, these become curvature-dominated theories. Where curvature plays a role, the residual cosmological constant plays a role. That was in the finite piece. Remember, we cancelled the divergent piece. This is the finite piece of T mu nu. And they give you a very good fit with the matter density being completely suppressed. Now, how that works, I can explain it to you, but that will take me a bit of time, so maybe I'll just state it, that that's discussed in my papers. But yes, in this theory, omega matter, what happens is, in this theory, lambda actually can be big, but its effective coupling, remember the coupling is that the phi squared r alpha alpha, that coupling turns out to be suppressed.
So then it's omega, the effective omega matter
is completely negligible.
Also at earlier times? Or
no. This theory has the following structure. Very early times, matter dominated. Intermediate times, curvature dominated. Late times, cosmological constant dominated. And so you can go back and you can remember, what was the original flatness problem? The original flatness problem is the early universe is matter dominated. So how can omega m be 0.3 today? And that's the flatness problem. The answer to this theory is omega m evolves in a completely different way than the standard theory. It still dominates the early universe, but what you would expect of matter is that it very quickly, as soon as the universe expands, it very quickly goes to zero. So actually, we now are in the current epoch in this theory is curvature dominated, and the future epochs, if it keeps going, will eventually become cosmological constant dominated.
When you say very quickly, what's the time scale? What's the
scale?
There has to be a scale, right?
Okay, the answer is the scale is no, and I don't know it offhand. Yeah. I know the answer to your question is I know how R of t depends on t. I haven't looked to see what the actual numbers are.
But it must be really quick, right? I mean, this
no. It's been curvature dominated for almost 10 billion years.
Well, but how is it consistent with the CMB then? I mean, the CMB.
No. Okay. Well, all right. Now. Okay. In this theory, I'm in the following situation. I've only just begun to do cosmological fluctuations. I published the first paper on it, was in that big list. So I'm still on the way to doing the CMB. The distinction is, when we do the supernova, we're just doing the Hubble plot, and it's completely kinematics. When we do the CMB, we have to use some dynamics. And that dynamic says we have an idea of how big a standard ruler is supposed to be at recombination, and then we look to see how big it is today. In this theory, the standard ruler will be a totally different size, and therefore the inferred values of omega m and omega lambda will be different, but I have yet to do the calculation. So the question is, how could you possibly get a different theory? The answer is if you have a different standard ruler. And I have a different standard ruler because what happens in this theory is I don't need inflation because the universe is horizon-free. Even this universe expands so that all the universe is always in one horizon. Now, how it expands and how I do the fluctuations I haven't done. This is an honest theory. You're perfectly correct in saying that when I do the calculations, the theory might fail. I'm fully aware of that.
You don't really need to do the full fluctuations. I mean, you just want to get the sound horizon.
Okay.
Right, so you don't really need to do a whole. It's a very simple calculation.
Okay, I would love if someone could do this calculation for me. Yes.
Probably 2 lines and it'll fail.
Yeah, so there's another question. 1 second.
No, it's the same point, that it's the standard ruler in the CMB.
Okay, I will try to answer your question. I have discovered, working on this theory for a long time, that every time I've tried to do something similar to the way you do it in the standard theory, it's theoretically incorrect. There are subtleties in this theory which force me every time to have to revise.
So unless you have to revise like Compton scattering.
No, I don't have to. No.
That's the only thing that goes into those calculations. It's very simple.
Yeah.
If you know the expansion history,
look,
it's very simple.
Okay, let me try to say this. I am quite prepared to agree with you that these are straightforward calculations. What I'm not able to tell you is that they're straightforward for me.
You can sit down.
But they can be straightforward for you, and so I'd love you to do them. Yeah. Yes, I think it was John next.
Just a very nasty thing about the cosmological constant problem is that anything that produces a mass is raised to the 4th power, and you get destroyed because the mass is starting the electron mass. If you take the Higgs potential, d5 squared plus alpha 4, it's classical, you minimize it, you immediately produce a mass that raised to the 4th power kills you.
It doesn't kill you. It only kills you if it gravitates with G Newton. It kills you.
No.
But I don't have a G Newton.
Technically, if it couples the Higgs thing couples to gravity, anything that produces any phase transition,
Yes,
produces a mass goes for power.
that's correct.
And this is why it's so possibly difficult to get rid of.
No, I never.
In your case, you're saying we have conformal
Yes.
symmetry.
Yes.
And so when we do the practical physics calculation,
Yes.
which is really what's giving you trouble.
No, I've done them. I wasn't able to present them.
You're saying that this problem is cancelled out.
Yes, that's what I'm claiming. I'm not claiming it. I'm claiming that I've done the calculation.
But you do break the conformal.
Yes, of course. I break it in the vacuum. Absolutely. What I said before, I can't really do it in 2 minutes, but where are we? Yeah. What I said before was, when you give the fermions a mass, every mode shifts, because you go from k to the square root of k squared plus m squared. Therefore, the shift is infinite. Therefore, if the cosmological constant is generated by a mass shift, then it is infinite. If it's a double well potential and you go from there to there, then it's finite. But infinite is good news, because I can cancel that infinity against the infinity of gravity itself. So the result of this is, when I reorganize the series, and I'll just have to show you the answer, when I reorganize the series and give the fermion a mass, the z of gravity depends on the mass of the fermion that's induced in order to continue to do the cancellation. So what is really happening is, the bulk of the cosmological constant is infinite, because it's a shift in an infinite number of modes. And the one that we measure in cosmology is only the residual finite piece. Now, the finite piece in the standard theory is the whole story. And it's very big. So that's the way this theory is different. And what is going on is the cancellation must continue to occur. Now, the other thing that happens is this. In the standard theory, gravity couples to the expectation value of T mu nu. Therefore, gravity couples to the sum over the modes. So the source of gravity is an infinite sum. In this theory, it's mode by mode. Each mode of gravity couples to one mode of the matter field. It's not one mode of gravity couples to all modes of the matter field, and that's where the infinity goes away. And that's the big change.
One more question? One more question.
Yeah. So I got the impression you oscillated a few times. I mean, is the Einstein-Hilbert term induced or not? I thought you said it was induced.
No, I didn't say that it was.
You just wrote it on the transparency.
No, okay, what I said was that Maldacena made a study of conformal gravity with a very special boundary condition.
I'm thinking about in your theory. So in your theory, when you couple your C-squared theory to standard model,
yes,
then calculate loops, one loop correction. Is there Ricci scalar or not?
No. No.
Conformal invariance is broken.
Okay.
Right?
Okay, let me be very careful. I don't induce an Einstein term from... when I showed you that I induced the R squared term by doing the fermion loop, that fermion loop does not give me a Ricci scalar. But that fermion loop, when the fermion mass is self-consistent, gives me the m squared R alpha alpha term.
So m squared has VEV then, right?
Is a VEV of psi bar psi. Yes.
Right. So that's a number.
Yes.
So then you have a term in your theory, you have a term which is number times Ricci scalar.
Yes, that's...
So that's Newton's constant.
No, it's not. No. It's not Newton's constant.
Of course it is.
Newton's constant is the coefficient of 1 over r. It's not the coefficient of the Ricci scalar. In the Einstein theory,
I take a source here, and I shape this source, and it will radiate with that leading approximation.
Okay, I have written papers to explain why that Ricci scalar term is not the Ricci scalar term for low energy gravity.
that doesn't have anything to do with curvatures and stuff like this. Just linearized on empty space.
But I have to
shaded source.
No, I linearize the C squared.
You have to linearize both.
Yeah, no, if I linearize, well, I've done both. If I linearize the C squared.
So you have Einstein plus something.
No, I don't have. Okay, never mind. I've stated what I have. I don't have to.
I disagree. Sorry.
Well, I've done the calculation. How can you disagree?
Yeah, well,
I've published the calculation.
Now in 5 minutes, this is hard.
Okay.
Maybe we should do it in 5 minutes over lunch. So let's thank Philip one more time.